Here is Baji, Suji, and Fuji. They're about to get a snack, so I thought we could go live for a little bit here. Thank you, everybody who is joining. We have not gone live in a hot second, so sorry about that, and thank you so much for joining. We look forward to seeing many of you today, our old friends as well as new friends that we hope to make today here. So, we have gone live. We will share the live on my other device so that I can see what's happening. Death Dragon, hi. Thank you for joining the live and thank you for liking the live as well. Here is Fujisuji Baji. We're here. Who's ready for this live? Oh, look at Suji taking care of Baji. We're having a peaceful evening. It is a rainy night today. Um, in Boston, it has started to precipitate. We will get rain until the morning, and then we might even get some snow. So that's what's going on. If you hear the rain, it is the natural rain sounds and not the hi, Baji, and not a fake rain sound, because sometimes fake rain can be good too. So here's all the books that we've been reading on the channel that we have been referencing and discussing. And here are the kitty cats. I'm going to share the live and start setting up my tea because we usually do a peaceful kitty and tea time and catch up with everybody first before we go and do more discussion. So once again, thank you for being here. Yay. Death Dragon, how are you? Ooh, and I promised them a snack as well. So I'm gonna do that. Let's see. Actually, I'm gonna let you see. I'm gonna come over here so that you can see everything. They're gonna get a little snack, and we will set that up just now. Hi, everybody. Hi, how are you? How is everyone doing? Suji here is asking for a snack, and they are all here getting one. And so, Baji, you want to share? Baji, you want to share? Baji, you want to share? This one's yours. This one's yours. Hi. Hi, Suladeep. How are you? How's everybody doing? I'm going to share the live. If you could share the live too, that would be amazing. It's a rainy evening in Boston. We're just getting started with this live stream on this channel. If you type a comment, I'll call out your name and comment. So yeah, Suladeep says, yo. Death Dragon says, hi. Twyla Hoskins, thank you for the emojis. How are you doing? So we are going live. We're just getting started. So usually we stay on the live for a long time. So you're welcome to hang out with us. We are currently catching up and hanging out with the kitty cats. I'm going to make some tea. It'll be a peaceful, soothing tea time with kitty cats. And I also cover physics on the live. So the topic is kitty cats and physics. So, but at first we just kind of catch up with everybody so that everyone is welcome and everybody gets to say hi, and we read everybody's comments in the beginning. At least pretty much we read it throughout the live, but especially in the beginning. Twyla, thank you again for the emojis. Combat Sport for Real says, hey, how are you? What is the topic? So I just mentioned we have been reading a lot of physics topics, actually. That is my background as well. So, real says, whoops, that's my iPad telling everybody. So we have been talking about both quantum and relativity. We actually covered a book called Einstein's Cosmos by Michio Kaku, and over there, we covered with a lot of time, actually, Einstein's special theory of relativity and general theory of relativity, as well as quantum mechanics developments in the 20th century. So it was really interesting. We actually finished that discussion, and we moved on to the 21st century topics like dark matter and dark energy. Although dark energy was something that came during Einstein's time, of course, he sort of helped to birth it in that sense. But Flavia Eduarda says, hey, hi, Flavia. Twyla says, I love the cats. Thank you. Yes, they are the main hosts of this channel. Sometimes I show my face when I feel like it. Sometimes I'm just like, whatever. So they definitely give you the visuals here mostly. Them and their activities. Ace Wolf Peach says Michigan string theory. Ace Wolf Peach says Michio Kaku string theory thoughts. Yes. So we got into string theory towards the end of the book, Einstein's Cosmos. So we can just, we could touch upon that today during this live. So I try to get a feeling for, yeah. I try to get a feeling for what people are interested in hearing about, but generally speaking, we also generally have sort of an idea what we'll talk about. Today, I'm kind of doing an impromptu live. I don't have a lot of like a whole lesson planned out or anything like that, so we can talk about these topics that have come up so far. Dark energy is just an X to replace. We don't know why all the galaxies go away. Yes, so we saw that during Einstein's time, he introduced actually the cosmological constant because as he worked on general theory of relativity, which is basically a generalized theory of relativity going from special theory of relativity because the special theory only worked for inertial frames. So for general theory of relativity, he knew that he was motivated to come up with it because he knew that, of course, you need to be able to explain accelerating frames as well and gravitating frames. And so he worked on it, and then he also had to be faced with this difficult question that even Newton had been faced with a while ago, which was that if gravitation is the main force in the universe and that's what's governing everybody and everything, then why doesn't the universe collapse on itself? And he had to introduce what we call the cosmological constant in his equation to kind of stabilize the universe, which later on gave us this concept of dark energy because apparently the universe is not only stable, but it's expanding, and it's not only expanding, but its expansion is accelerating. As above, so below. What about the new news about neutrinos and the Large Hadron Collider? Is that what you're saying? As above, so below. When it comes into existence, it must return to the void as well. Is there three cats? Twyla Hoskins. Thank you for asking. You should. You will have to stay in the live and confirm for yourself how many cats you see. So, welcome, and thank you for joining the live. We have a famous French physicist saying dark energy doesn't exist, but negative mass explains expansion. Can we see you speak? Well, you can hear me speak. I think that's probably enough for now. But I do appear in my videos sometimes. Maybe I'll rotate the camera. I don't know. Haven't felt like it yet. Twyla Hoskins says, okay, thank you for being here, everybody. Here's the main show host, Baji, right here. So I actually don't know if negative mass explains the expansion or not. So the material that I have been sort of referencing, since a lot of the physics and a lot of the research is still evolving, it's, I don't want to sort of go into conjecture of what may or may not be, although, if we want to have a healthy discussion on it, that's totally fine. But since I do sort of present the material sort of in a teaching kind of way, I want to, cover things that are pretty well understood. So I've been referencing textbooks and even something like dark matter candidates, which I know is not the same as dark energy, but I'm just giving you an example of something we've covered. Dark matter is something we don't know what it is, as well as dark energy. Exactly. They're two different things, but dark energy is sort of what we need, as you said, to explain the cosmological constant, this placeholder term that Einstein had to introduce in order to stabilize the universe, but also now observationally we know that we have an expanding universe. So because we don't really understand why we call that dark energy, but then dark matter is the number two most biggest question of the, or big open question of the universe after dark energy, I would say, because dark energy is most of the universe. And in dark matter, I subscribe. Thank you, Twyla. Thank you so much for subscribing. For dark matter, because we have also observational energy, and seems like more like a missing mass kind of thing. It's more of an astronomy and or particle physics type of question, whereas dark energy is more of a cosmological question. Cosmology researchers are trying to figure out and confirm the expansion and figure out what could be causing it, whereas astronomers want to figure out, what types of objects or where in the galaxies, including our own galaxy, there seems to be this invisible or dark matter. And also particle physicists want to know what is the particle nature of dark matter. If it's just another type of matter, then we should be able to find it in a particle physics type of experiment. So I think that's sort of where the collider stuff comes in. We want to set up certain experiments to be able to maybe give us an experimental result or experimental evidence of dark matter. Something like, hi Fuji! Fuji's crying. Dark matter is the X to explain why stars far away from the galaxy black hole result. Yes, so we talked about, it's actually, that's a great point. Let me show you the exact plot. But yes, things far away from the galactic center moving fast is an issue. And are you a professor? I'm not a professor at this time, but I have been in research and teaching in the past. Is the collider in Illinois up and running again? Are you talking about Fermilab? I know Fermilab is outside of Chicago, so that could be the one you're saying. I actually don't keep super up to date on all the different colliders. I just know that, ooh, look at this. So we actually referenced this chapter right here. But yeah, so as somebody mentioned already, combat sport for real, actually. Let's look at exactly what he's talking about, or she is talking about. I just want to be a little bit more specific. So there is a supermassive black hole in the center of the Milky Way galaxy, and in fact at the centers of a lot of other galaxies as well. But basically, the more specific way of saying this would be the galactic center. We expected that most of the mass would be contained within sort of the same distance, sort of where we are, within that radius of the galactic center. And this has to do with our observation of luminosities, and all the luminosities seem to be accounted for within that distance. It was around 8, around 8 or so kiloparsecs. So, some people round up and say 10 kiloparsec is the radius of of our galaxy. The kitty cats do sleep in the same bed. Yes, if that's what you're asking. They sleep wherever they like, and I sleep also in my bed. So I subscribe. Thank you, Twyla. Thank you so much. So, when somebody asks you what is the sort of size of our galaxy, in case you're interested, our galaxy from one end to the other is around 100,000 light years. That's not very big, not very small. It's a pretty beautiful spiral galaxy and quite large. It's not a dwarf galaxy, it's a normal galaxy. But as far as the radius goes, we're not, we're sort of off to the side of our own galaxy. And sort of where we are is around 8 kiloparsecs, and the overall radius is around 10, 11-ish kiloparsecs. So So basically, according to, so this is sort of where the astronomy angle comes in. You'll notice that now we're talking about in astronomy lingo, kiloparsecs and galactic center, and these types of things are more of an astronomy lingo. So in astronomy, we kind of knew from observations where the luminosities are. And we're thinking that the objects that contribute to those luminosities are going to be basically what contribute to the mass in the galaxy. And based on what we know, we expect the orbital speed of things away from the galactic center to be going down. But instead, we see this behavior, which is what I think Combat was talking about. So orbital speed in kilometers per second versus distance from galactic center in parsecs. And you can see where the sun is. The sun is at 8 kiloparsecs. So that is our sun. We're not, super close to the center. We're kind of off to the side, like I was saying, and we're at 8 kiloparsecs from the radius, or sorry, from the galactic center. So we were expecting that rotation of our, this is rotation of our galaxy compared to Keplerian system. We were expecting that, if things were all normal, we would see the orbital speeds to go down because most of the mass we thought were in the center or within a certain radius from the center. So I'll read this sentence. Most of the galaxy's luminosity is provided by the disk, whose brightness falls off exponentially with a scale length of around 3 kiloparsecs. Thus, most of the galaxy's luminosity lies inside the sun's orbit, and the sun's orbit is around that 8 kiloparsec number that I was saying. Because the sun, the thing that we go around, also goes around the galactic center at a radius of around 8 kiloparsecs. If most of the mass lies inside the sun's orbit as well, we would expect the mass to be around a constant for r greater than r naught, and hence we would expect the orbital speed to kind of fall off and go as r to the minus 1/2. So this is the big mystery, and people were a little, baffled by what they found, which is that this is not, this is strange behavior. And it led them to think, oh my gosh, is there actually more matter than we can account for? And since we can't see it, it's not contributing to the luminosity. Maybe it's sort of, that's what lent it the name dark matter or invisible matter, or sort of like almost like transparent matter, something that does not interact with photons and give us luminosities. So that's where all of this comes from. And this is one of the evidences of dark matter. When people give talks on dark matter, this is something that they normally show. So notice how I used a textbook. This is the Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson, astronomy professors at Ohio State. Last time I checked, also were former colleagues of mine when I was a student there, grad student. So basically, I'm talking about, so I understand that dark matter and dark energy are current hot topics of research. So I'll try to mention on the channel when we talk about it, things that we kind of already know for. Yes, Fuji, come baby. Fuji has brought me a toy and he wants me to notice that. Come, Shona, asho, chole asho. Oh my goodness, Fuji brought me a toy. Oh wow, oh, thank you so much, Fuji. Thank you so much. I'm so thankful. Thank you. Where is your accent from? Not Ohio, Lily. Well, Ohio, I went to grad school. So, it's common for academics to not be where they're from. So I'm from India. Originally, I was there for 18 years after being born there. But then I've been in the U.S. In all kinds of places. So I've lived in North Carolina for school, Ohio for school, Ohio for work, and now I'm in Boston, Massachusetts. So Andromeda is coming to merge with us. Yes, we are going to be eating Andromeda. That's okay. Andromeda is MIT. I did work at MIT, yes. Yes, I did work there. Yep. Yep. Part of my background, indeed. So until September, I was at MIT. So, anyways, unfortunately, not no longer with them at this exact moment. But oh well. Basically, I'm trying to give you some examples and quotations or material to talk about. Like when we go to talk about dark matter and dark energy, I'll make sure it's from a good source, like a textbook that is taught to astronomy majors or cosmology majors or astrophysics majors, things like that, so that you know that the information is coming from somewhere that is what do you call, trustworthy. So, for example, we talked about dark matter candidates. And, the fact is that anything could be a dark matter candidate at this point until they confirm it. Unfortunately, no dark matter has been detected. Sorry, I have to go to bed. Twyla says, bedtime. Good night. Hello, namaste. How are you, miss? I'm good, thank you. So, as you said, dark matter, we have not confirmed exactly what it is. It's an astronomy question, it's a particle physics question. Mostly these two types of fields kind of pursue it. And if you become a PhD candidate yourself, you'll probably have the opportunity of pursuing it as a topic. So there's a lot of papers that get published all the time, I should mention, about both dark matter, dark energy, all of these things. I really think dark energy and dark matter are the top two open questions. So I've been taking some time to communicate about that on this channel because I think as scientists, it would be nice to, I don't know, say a little bit more and more clearly what things we have actually accomplished so far. And also the 20th century was so interesting and such a great progressive time in physics that it was also a lot of fun to cover it. But that also gives you like what things we have covered already and what things is left to cover. So dark matter didn't really come up too much in the 20th century main developments. Dark energy came up in a very interesting way when Einstein was talking about, or Einstein was trying to understand the universe at a cosmological scale and gave us general relativity. Over 100 years later, we still don't know what dark energy is. So I think it's obviously a pressing question. We are still working on it. But that's sort of the intent, is that we'll talk about the things that we have already worked on, amazing discoveries that we've already made, including in quantum mechanics, of course. But we'll also talk about things that we don't know yet, that we're still working on. And so that too will be made available to you in case you're interested, and go off and do your own thing with it. So, Ace Wolf Peach, message retracted. Okay. So, yeah. So basically, maybe we'll talk a little bit about dark matter candidates because I mentioned it already today. And you'll see what I mean when I say that we're going to use the textbook and give you some information that is more to be trusted. Because sometimes when the papers come out, it's not necessarily super confirmed. A lot of theory papers might come out with a dark matter candidate or some math, but really it would have to be confirmed in an experiment, like a particle physics or astronomy experiment or observation, for it to become real. And as some of you pointed out already, dark matter has not been confirmed yet. We don't know the physical nature of it yet. It is still an open question, a very big one, of course, but still an open question for us, you, anybody to work on. Same thing for dark energy. They're two very different topics, though. So at this time, since I already have the page open, on lives, how often? How often do you speak? So I have been going live on most days. I took a little bit of a break and I went to New Orleans. So I took a bit of a break, but I go live, Wednesday, Thursday, Friday, Saturday, Sunday. Sometimes I take off on Monday or Tuesday, usually like nighttime. Sometimes I go live in the afternoon too, or evening. But this type of time is pretty common. Friday has been a big one for going live as well. So yeah, catch us anytime, any of these types of days. Also, feel free to go and look under the live tab on my channel. The channel is about kitty cats, but also the lives are about like physics. So you can click on any of the live videos and listen to it. And we've covered a lot of stuff. Sometimes the titles don't really reflect physics, but I've been trying to do a better job about that because sometimes the live kind of develops more organically, depending on the interest of the people. A lot of people really, really enjoy the 20th century physics topics, and we covered those at length. I'm not saying I went into like equations. I tried to. At one point, I was going into the equations, and I saw like people were kind of dropping off. So it's more done at the level of a popularized science level. Like it's not done as a literature review of science kind of level. So a lot of these discussions we've done already. And I really encourage you to find those videos in the past, in the past live streams, if you want later on. Not now, because now stay here. But under the live tab of my channel, you'll find a lot more physics topics on the live videos. So basically, because there was this mystery, we just talked about the mystery of the orbital speeds not falling off as a function of the distance from the galactic center, even in our own galaxy, Milky Way. And basically, you can imagine when people would first find this issue, and they're also making advances in particle physics. So 20th century saw a lot of... Are you joining NASA? Well, I worked on a NASA project for my PhD, but currently I'm not affiliated with NASA. Thank you. On lives, how often are you joining NASA? 12 watching. Oh, thank you so much. Yeah, thank you for your support. Really appreciate the people who are here and liking and sharing and subscribing and all of that stuff. Thank you so much. So let me recap a little bit about what's been happening in physics in the 20th and 21st century. This is my favorite topic. I can talk about this all night. Generally, it really depends on you, how long you stay, and I'll keep talking about it. So basically, we know that Newtonian mechanics was something that worked for a very long time. He did a really good job in the 1800s, Newton that is, and gave us classical mechanics and also the Principia, which is of course a great book, amazing publication, and that gave us calculus and other useful things like that, as well as a little bit of optics work. So he was really versatile, amazing scientist, very introverted, worked by himself and his dog, Diamond, and gave us Newtonian mechanics or classical mechanics. This was very sturdy, very stably able to explain our world and give us equations that we still use. In fact, NASA still uses Newtonian mechanics to launch things into space because, for the most part, for the scale of classical scale type of business like you, me, cats, trees, the moon, the earth, comets, pretty much at these scales, Newtonian mechanics actually works wonderfully well. So, yes, Newtonian mechanics book again. Diamond burnt his papers. Yeah. Diamond probably wanted attention, just like Fujisuji Baji. Baji's mouth is open because he is, he is engaged. Basically, Diamond probably wanted attention, is my theory on it. Newton was kind of busy, so Diamond probably wanted him to give a little bit more attention than he was receiving, so he burned some things. But anyways, all of that was to say that Newtonian mechanics was very successful. But then, pretty much in the 20th century, we saw a lot of developments, and we needed these developments, and it kind of really, really mega shifted our paradigm and our understanding of the world and this universe. So especially with Maxwell's work and electromagnetism developments, seeing the electric and magnetic fields and their nature, and the fact that light is a wave and it's a oscillating electric and magnetic field. And then the question of, well, if it's a wave and it's made of electric and magnetic fields, well, what carries light to us from these distant objects, for example, in astronomy? Because remember, astronomy is as old as, anything. So the fact is that we've been doing astronomy traditionally with visible light for a very, very, very long time. So we know that we can see things that are out there in the night sky, things that we call stars. Most of them are galaxies, but whatever. So we kind of know that we've done traditional astronomy for a very long time, so we know that light is coming to us. So when electromagnetism developments happened I'm just kind of summarizing, for you here. When electromagnetism electromagnetism developments happened by Maxwell, people like Faraday, who actually did experiments in the lab to show you like how electric and magnetic fields were behaving and changing into each other, things like that. Those developments were very path breaking. And Einstein was a very good student of all of this. He was a very he had a unique learning style, and he actually struggled in his early career to find a good position, even to find a good spot as a student or as a researcher. But he was actually an excellent, literature reviewer of other people, as well as very brilliant himself, and he continued to contribute and stay very interested, even with a study group and things like that, even when he did not have a formal appointment at a university. So all of that is to say, Michael Faraday's work is necessary now. Yeah, yeah, I love Faraday. Faraday, Michael Faraday. So do you search for the emerald tablets as well? I'm not sure what that is. So you'll have to explain what that is. But yeah, Michael Faraday, lovely, lovely person in the sense of his experimental. People like Faraday really show that physics is an experimental science, because all of the electromagnetism theories and equations would be nothing if we didn't actually get to see this in real life. So all of the confirmations and experiment that followed and that happened around that time were extremely significant. So anyway, all of this actually led to a confusing state of affairs, which was that people thought that you needed something like ether to propagate light. The fact that light is a wave and it's coming towards us from these distant things gave us these confusions, which is that, oh well, if light is a wave, well, what is waving? People understood, for example, sound waves. Like sound waves don't really travel in a vacuum. You need some sort of matter in order to be able to propagate sound waves. So people's sort of perception of what a wave is and how a wave will wave, as in how it can be waving, was sort of limited at that time, and they struggled to understand how this light was waving. And all of that actually led to a more updated, more correct theory of light, and which brought everything together with electromagnetism, which is, of course, Einstein's special theory of relativity, and gave us the relative nature of space-time and mass-energy equivalence. And he had a very productive year in 1905, including this work that I just mentioned, as well as photoelectric effect and Brownian motion. So in a nutshell, 1905 was amazing. He gave us all these amazing contributions and publications, and we were sort of transported to a different world. And the fact that photons, photoelectric effect, as in photons shining on metal, giving us electric current, something that we still use, of course, solar panels, things like that. That, of course, is what we call the old quantum mechanics, because that gave us the quantum nature of light. So Einstein, fathered relativity and godfathered quantum mechanics in that sense. Of course, there are other great contributors to quantum mechanics before, after, and during him, but he's been given credit as a godfather of quantum mechanics for his work with light and its photon nature. But so all of this was happening in the 20th century. So really great topics. These are amazing. And we read about this from Einstein's Cosmos by Michio Kaku. And we covered all this in great detail with a lot of very nice discussion, very healthy, amazing discussions. And then we started to see the bizarre, developments, of course, in quantum mechanics also at that same time in parallel. And we saw the great debate between Einstein and Bohr, all of that. And pretty much life is pretty good in the 20th century because it's been so long already. So we've kind of covered and understood, all of that. Nubita is asking, can you say about the topic of your thesis? So my thesis was in particle astrophysics. I didn't talk about it too much yet because I was busy covering the 20th century. I like the 20th century because it sets up everything, obviously, for now. I mentioned, I was just about to get into it, actually. So all these developments in quantum mechanics and then subsequent confirmation of it, because, we started to actually look at an atom and understand, oh, wow, the atom is not fundamental. It has this nucleus. Oh, wow, the nucleus is made of protons. Oh, wow, there's also a thing called neutron, because the neutron was discovered later on. and the nucleus is not fundamental. And turns out actually now that the proton is not fundamental in the sense that the proton breaks down to quarks. So those types of things. What I'm trying to say is some of the particles we've discovered later on, it's more of a 21st century thing, but the 20th century is the backbone of all of this. Because of so many developments in quantum mechanics, we were able to basically establish this whole new field called quantum mechanics, which is the physics of the very small, which developed along with the physics of the very large, or the physics of the cosmos, which is Einstein's relativity and general theory of relativity in particular. So it was a very amazing paradigm shifting rich time, and that's why I spent so much time talking about 20th century physics, because so much was happening then. Now, of course, we have also a field called particle physics, but where did it come from? Of course, all of the work and foundation that was laid in the 20th century in quantum mechanics is what gave rise to its own another sort of whole field called particle physics, and the standard model of particle physics, giving us families of fundamental particles. And because there's still things that we don't understand, there's even beyond standard model or BSM type of physics that there are people who do their careers on just that. So you can imagine that the richness of all of this is like a lot went down in the 20th century, and a lot has come, about since then. And we have, entire new subfields of physics. Particle physics, most notably, is one that has really, really started to dominate. So if you see a lot of particle physics experiments, just know that quantum mechanics was considered the weird topic in 20th century. There were people who thought it was the weirdest thing. It's so bizarre. It's not good. We don't like probabilities. We don't like uncertainties. We're used to deterministic results and answers. Like when you tell me the position of the moon, I can tell you it's future position up to like 1,000 years, and that's only because I get tired. That was the nature, that was the attitude of physicists at that time when quantum mechanics was developing. And here you were saying that the wave equation of an electron is only the probability of finding that electron. You know what I mean? It's very different. It's very contradictory. It's very opposite. Very magical, mystical. People were not comfortable with it. A lot of the tensions and dramas that went down in the 20th century was because physicists even the physicists who contributed to quantum mechanics were not comfortable with the beast that they had contributed to, the monster that they raised, in the sense of how different it was in comparison to everything else that they knew so far. So, So that's kind of how the 20th century happened. There was a lot that went down and shifted our realities. I wanted to say this because the 21st century is kind of different. Even though we have made progress, especially like I was mentioning in particle physics and setting up a whole new, system, if you will, of particles and things like that, I would say we haven't really done a lot of paradigm shifting, reality shifting type of work. It's more the case that the place where things have really, really shifted and made sort of a heaven and hell kind of difference is in observation, experimentation, and measurement. So we measure a lot better than before, we observe a lot better than before, and we experiment a lot better than before. We have these gigantic, amazing, awesome experiments that cost a lot of money, and lots of big collaborations of people across the world work on them. And so that's the sort of thing that's changed a lot, and that's giving us confirmations and results of some of the things that were really 20th century predictions. So I wanted to just mention that real quick so that you have a little bit of a basis of what's been kind of going on in these two centuries. The 20th century versus 21st century is very different. What we do nowadays is very different than what we used to do. And a lot of people are very, of course, busy with the experiments and things that they're finally able to do now that we have that better technology and things like that. They're also busy designing future experiments as well. So if you're wondering what are scientists doing these days, it's kind of different now. It's not the same as before. And of course, you'll see a lot of theory papers on dark matter as well. Things like that, because dark matter is still an open question. Of course, people can work on it and they can publish their results on it or even their theories on it. But really, it's up to an experiment to then confirm the theory or not. Do you believe carbonado diamonds are extraterrestrial, as Dr. Stephen Haggerty of University International Miami University? Carbonado diamonds. Really know nothing about diamonds, actually. I mean, I know something about diamonds, but not what this topic is. Nope, I don't. So, actually, that's a great point. You know, physics largely at this point has some subcategories. There is something called condensed matter physics, laser, molecular, and optical physics. Of course, our good old astronomy, astrophysics. Particle physics is a big field now as well, as you'll see lots of things going on. And then, of course, there's also string theory. So somebody asked about string theory earlier. I just want to give it a little shout out here that string theory is a much smaller effort these days. But it did come up in our discussion during our previous lives. So something like general relativity, once you kind of write down the equations for that, for more dimensions, and you allow sort of your imagination to think up more possibilities with what can happen with these higher dimension type of physics, it really kind of gives birth to something like string theory and superstring theory. So now, because superstring theory is not confirmed with an experiment, because it's very difficult / maybe impossible to experiment it, it's rather unfortunate it remains as a theory and it's not got the credibility of an experimental result, if you will. I'm not saying that superstring theory is not real and lots of real people, very good people, work on it, but it's just suffers from the lack of experimental confirmation. And I think maybe that is the reason why I find a lot less people work on those more theoretical topics. And something like the grand unified field theory we talked about, you know, some people, especially string theorists, of course, will say that the superstring theory is basically a good candidate for the grand unified theory that Einstein was working towards. Some more general theory that unifies our understanding of electromagnetism, relativity, and even quantum mechanics. As I was saying earlier, a lot of people didn't really like some of the repercussions of quantum mechanics and its approach. Even though quantum mechanics stands true, given experiment and observation, and it's been very successful. But a lot of people are not comfortable with its approach. It's the physics of the very small. It explains the dynamics of small things like an electron. But a lot of people don't really like its probabilistic and uncertainty by nature sort of nature. So they thought it would be good if they could, and also those same people might not like particle physics because particle physics gives us a whole different families of particles. It's this like, you know, people getting Nobel Prizes for a particle every year type of thing happened at one point towards the end of the. When do you get your fields metal? When do you get your fields metal? Do you mean metal? Thank you so much. So you know, particle physics again, it has come a long way and it has given rise to the discovery of lots of things, you know, particles pretty much. But something that people minded, something that people did not like about particle physics, of course, is the fact that it doesn't really, you know, it doesn't give you a more unified, deeper, broader understanding of the universe. It just gives you one more particle, one more particle, one more. It's sort of, it felt like, you know, particle physicists probably don't mind this, but other people might have felt. I'm giving you sort of how the field thinks broadly, you know, not just one category of physicists, but all categories of physicists. So the theorists or more classical physicists or general relativists might have sort of not liked that particle physics as a theory is not really giving us a more broader understanding of nature. It gives us one more particle, but what is it doing to unify relativity with electromagnetism, with quantum mechanics, and all of that business? You know, now of course we've understood more about this universe with particle physics as well, but depending on who you ask, there might be some politics. So also keep your keep your eyes open for politics as well. Sometimes when you hear an opinion and you hear something, it might be a politics within the field, giving you some sort of sense of that particular subfield. So in on this channel, I try to stay very neutral and kind of present what we know and what we don't know. As a matter of fact, it's not so much that I have an emotion associated with something versus other. And if I do, I'll tell you. So I do have an emotion associated, for example, with the particle that I worked on, neutrinos. Sort of an emotion, I guess. I mean, it's been years since I defended that thesis, so it's not like a big deal anymore, really. But I worked on particle astrophysics, as in astrophysics that's done with particles other than light. In my case, it was neutrinos. Neutrinos is a type of particle. It's since someone asked about my thesis. Neutrino is a type of particle, metal. Oh, good. Oh, thank you. Thank you. I think that's very difficult to win. But thank you. Are you teaching at Harvard? Not right now. You should tell Harvard to hire me, though. Neutrino is a type of particle. So since one of you asked about my thesis, I'll just tell you real quick. So since I've given you the very speed summary of the 20th century, the speed summary of the 21st century so far. The two biggest open questions: dark matter, dark energy, not in that order, reverse order. Dark energy, then dark matter. And you know that we have discovered lots more particles. Some people are kind of upset about it, actually. And well, we still don't know the particle nature of dark matter, and we still don't know exactly what dark energy thingy thing is, whatever, that type of stuff, right? That's the current status. But we have come a very long way in experiment, measurement, observation. Kudos to all the instrumentalists that may ever hear about this live, or who do anything with anything. I really love the hardware people. They have done everything that is worth mentioning in the 21st century. So I'm sort of have a bit of a bias towards that as well. So I should mention that now. I said it's a mostly neutral channel, but I probably do have a little bit of a bias towards people who are instrumentalists, because I feel like in the 21st century, their contributions are the ones that have made or that's the make it or break it kind of contributions in this particular time. I don't think we've done anything too paradigm shifting or physics understanding or nature mind blowing since the 20th century. And the things that have come a long way have all done so because of the great leaps in experimental work and observation and instruments. So that's why I say, there is that. But basically, since one of you asked about my thesis, so real quick, we've done astrophysics and astronomy. Astronomy is more of a how should I put it? Astronomy is a study of the heavenly bodies, something like looking for aliens, something like looking for. When I say looking for aliens, what do I mean? Something like looking for extraterrestrial life or other planets that are Earth-like. That's sort of an astronomy question. Okay, so I kind of wanted to define out what is astronomy versus astrophysics. I've done both, so I can tell you sort of my view on it, on the difference between these two things. So astronomy, something like working, so in case you're interested in working on it too, this is hopefully helpful to like future PhD candidates and grad students and students. So if you want to, find your calling or understanding of what you would like to do, this is hopefully helpful. So astronomy, like something like, say, they found a bunch of planets that are kind of like Jupiter. They were looking for and hoping to find planets that are more like the Earth. That's an astronomy topic. And it's kind of related to the alien thing, where we hope to find planets that are kind of like Earth. Reese, how are you, my friend? Hello. Yay, physics people are in the chat. Good. So physics, sciencey, engineering-y people are in the chat. I love it. So astronomy, say if you really had a burning question about extraterrestrial life or something, say, on Mars, or, well, Mars is probably more of a NASA thing. at this point. Or say, so I'm just kind of giving you the feeling of it. If you are interested more towards the engineering side of things, how to put something on Mars or how to go to the moon or doing things with the moons of Jupiter, Europa, for example. I know Jet Propulsion Lab is like crazy about Europa, or at least they were. I don't know at this exact moment, probably still are. So if you're more interested in the engineering side of things, the labs like JPL, NASA, those places are more going to be your place. But say if you want to do research on finding, like gathering a bunch of data and then analyzing the data and then reporting on whether you could find a planet that is kind of like Earth or not, but really you found Jupiter instead. Not Jupiter exactly, but maybe you found a bunch of Jupiter-like planets. Well, now you still have to do the analysis and report it and tell us the results and publish it and archive first and then some other journal, then that's more of an astronomy activity, okay? So, pretty drunk, how are you? Oh, wow. Hi. Hello. I'm good. Pretty drunk. Goodness, is it your birthday? Hey, Google, what day is it today?
Today is Thursday, December 5th.
So, yeah, we'll see if it's Reese's birthday. If it is, we'll say happy birthday to him. So that's more of an astronomy thing. Now, astrophysics, what is astrophysics? Astrophysics is where, say, that stars die and they make supernovae sometimes. They make supernovae a lot. The death of a star sometimes involves a big explosion with gravity, the star kind of collapsing on itself under gravity. And all of that energy, all of that mass, all of that everything going on within a star leads to basically a massive explosion. Depending on how big the explosion is, it gets different names. It can be supernova, hypernova, gamma ray burst. Gamma ray burst is sort of something that is really, it's associated. It's basically a stage of a hypernova, but I get into too much there. Basically, understanding the physics within one of these environments. Say, I mentioned a few things, right? Say you want to understand what is happening within a supernova, how a star dies, how it goes through its different life cycle phases. It's sort of in the intersection of astronomy and physics, and understanding the physics within these environments. That's more of an astrophysics thing. So, no, my friend who I hardly ever see these days asked me to go for a couple of drinks, so obviously I had about 6 pints. Oh, I see. You're talking about the friend who you hardly see. I thought you meant me. I know I haven't gone live in a few days, so I feel guilty about that. But you're not talking about me. Got it. My friend who I hardly ever see these days asked me to go for a couple of drinks, so obviously I had 6 pints. Good. Well, it's a British thing to do, right? I don't think that we know any different when it comes to the UK. He's still the same apart from his hair ran away. Aw. Oh, that's so nice that you caught up with a friend. Ace, Wolf Peach message. Don't see it anymore. Ace Wolf Peach said that I should get the Fields Medal and teach at Harvard. Please, everybody, write to Harvard and whoever gives the Fields Medal. Anyway, so I wanted to mention what astronomy was and what astrophysics was so that you get a flavor of what these things are, what these fields are. So understanding something like a supernova, maybe writing code to simulate a supernova, maybe writing code, that's astrophysics. Stellar remnants, we read about like after a star dies, it makes either a white dwarf. So by the way, depending on the mass of the star, of course, depending on the original star's mass, when a star dies, its ugly death, it either becomes a white dwarf or a neutron star or a black hole, depending on its mass. The more massive it was, it could even, you would need a very massive star, but it could even make a black hole, actually. So, it's this type of thing is sort of both astronomy and astrophysics, but really if you got into much more of the details of the physics of a black hole or the physics of the neutron star, then that would be in the realm of astrophysics or understanding how particles get super duper accelerated in a natural accelerator like a gamma ray burst. That's astrophysics. So myself, was interested in astrophysics. So I really love astrophysics, always did. In undergrad too, I worked on it a little bit. Uh, you know, in undergrad, I was kind of just bumbling around trying to do whatever research I could find. So it's not the biggest amount of time that I spent on astrophysics. I actually ended up working in a chemistry lab myself for the longest time in undergrad. And then I also did astrophysics. I also did a little bit of condensed matter. But I eventually, later on, after many, many rotations of different things, I ended up doing particle astro as my thesis. But I also did a little bit of cosmology. Well, actually, I did almost a year plus of cosmology, and also I did a tiny bit of condensed matter. So that's why I'm able to kind of cover a lot, because I have experience with more things than most people do. But I also know what I don't know, which is that I don't really know condensed matter. I couldn't tell you about diamonds and carbonado or whatever, because my interest is not too much into the materials side of things, material science, materials engineering. That type of stuff would be sort of the more known field within physics, which is related to condensed matter physics. I don't know too much about it. The only thing I got into a little bit was graphene, and that was it. And then in undergrad, I worked on thin films and how thin films behave on various occasions. So not really. I just wanted to give you. I've mentioned this on the channel before as well, that I'm not a condensed matter person. I'm more of a astrophysics, cosmology, astronomy, physics person. So anyway, my thesis, more particularly, I had to give you all this summary first before I tell you about my thesis, because my thesis is a more current thing, right? It's like talking about, oh, Baji, your food is about to fall. Yes, graphene. Mine is, yeah, it's weird how binge drinking is traditional here. Like literally poisoning yourself is normal. Yeah, but you guys can take it, right? Like, I thought people in the UK can just drink infinitely without a break and without. Yeah, I don't know where it goes. I have, I had British colleagues who just were able to drink to like constantly, and I don't know what happened to it. So, it's a British thing. I accepted it. Mine is structured lattice. Yes, graphene. That's like a single atom layer of graphite, right? Yes. So don't ask me too many questions about graphene because I forget. I didn't keep up with it. I don't remember all the things I learned about graphene. So, because that was like a lab I joined in my first year while I was also teaching and doing research and doing classes, coursework. And I probably, and I was so happy after my quantum final that I myself drank a little too much and blacked out. So I might not remember everything about graphene. So after that, I was much better about things and did not black out. So I can't take it. I feel absolutely. Oh, really? The structure of the lattice at the molecular level can redesign fabrication processes. Yes. So, fabricating these various materials is a big topic in condensed matter. Not something I went into myself, but if you want to share about it, I'll read out your comments for general knowledge of the people who join. I think it's all very interesting stuff. It's not something I did myself. But, yeah. No, I'm so tired, but I want to watch. Groove Toot! Hi! Long time no see, how are you? Here's Baji. Groove Toot has joined as well. Ace Wolf Page is going to tell us about the structure of the lattice at the molecular level of things, maybe. I drank a fifth of beam last night, painting a rendition of Dante and Virgil in the ninth circle of hell. Are you saying that you painted last night? Because that's a really nice activity. So anyways, coming back to what I worked on myself. So I worked on particle astrophysics. I just defined for you what astronomy is and what astrophysics is, sort of with examples. I was in the physics department, so it was more of a physicsy thesis, but I also collaborated and was in the intersection of astronomy, astrophysics, and particle physics. My advisor was from a purely particle physics background, so she made sure that I understood my particles. I had interest in astronomy, so I made sure that I understood astronomy enough. And then I also wanted to learn astrophysics, and that was also the research topic. So basically, traditionally, as I was mentioning earlier, astronomy, astrophysics, whatever, doesn't really matter too much about the differences, was done traditionally with visible light. Like we can just see stars and things like that with our naked eye. So that's called doing astronomy with visible light, optical light. But then, of course, in more recent years, we've started to do astronomy, astrophysics, both with other types of light, like gamma rays and X rays and things like that. So, pretty much, particle astrophysics is a field which it accepts into the field anything that's a bit more of a modern way of doing astrophysics with particles other than traditionally visible light. So, particle astrophysics could be something like doing astrophysics with gamma rays. Particle astrophysics could be something like doing astrophysics with X rays, although I would consider that to be a little lame. I would consider at this point to be just normal astrophysics. I don't know if I would go into the, calling it particle astrophysics. And then, of course, what is more than welcome into the club of particle astrophysics is doing astrophysics with particles other than light completely. So, not even a type of light, but a type of a different particle completely, like cosmic rays and neutrinos. Cosmic rays are charged particles that could be of extra galactic nature. They could be coming from a different galaxy. It's hard to tell sometimes where a cosmic ray came from because they're charged particles. They can get bent around by the magnetic fields of the galaxy and things like that. So there are entire groups who work on just cosmic rays. And then my group worked on neutrinos. We specialized in doing searches of high energy neutrinos coming from these astrophysical sources. So when somebody says astrophysical source, what they mean is some object or phenomena or event out in the night sky. And in this particular context, it's probably extragalactic. So it's not in our own galaxy. So that's what we did. So I worked on particle astrophysics with a focus on neutrinos, trying to detect and measure neutrinos coming from astrophysical sources, and it became more of a endeavor in neutrino detection work. And we used the Antarctic ice as a detection medium for these neutrinos to interact in. Neutrinos are very interesting particles. They're very weakly interacting, introverted particles. They're leptons. They're in the same family of particles as electrons, but they're not charged, and they don't interact other than with the weak force. So they don't interact most of the time. If you find one that's very energetic, you might be able to get something out of the neutrino, some sort of signature out of the neutrinos interaction, and generally you need a lot of detection medium in order to have any luck with finding a neutrino in the first place, or you need to be looking for a very long time, either for a very long time or at a very large volume of detection medium, or instrumented volume is what you would need for something like a neutrino. So pretty much a lot of my work also had to do with this type of thing, like just doing detection and instrumentation and understanding those types of things, and radio astronomy, because we actually were trying to collect radio waves from the interaction of the neutrinos in the ice. So it became this whole thing. And that's what I worked on, because one of you were asking. I know it can be a lot in the sense of once I start talking about it, there's really no end to it. There's so much to talk about. But that's what I mean by particle astrophysics. In my case, it was done with the particle called neutrino. And neutrino is also in this book. We were just talking about how the open questions of the universe right now are dark matter and dark energy. And in this textbook that we were covering, neutrinos were actually considered as a dark matter candidate. Neutrinos are so difficult to detect in comparison to some other particles, in comparison to most other particles, actually, that people, when they first realized that there is this missing matter, dark matter, invisible matter, whatever you want to say, in our galaxy, in our own galaxy itself, they actually thought that what if they're just neutrinos? What if there's neutrinos that we're not accounting for, and they are the ones that would be contributing to this missing mass? It turned out that even though neutrinos are weakly interacting, and so they, in that sense, they would be a good candidate, but they're very low mass, which makes them not such a good candidate in the end. And it would turn out that maybe they contribute to a little bit of that missing matter, but not most of it. So even though it's a very reasonable consideration of a dark matter candidate, I think it was pretty much considered and then discarded as a dark matter candidate. But that's to give you further context on what a neutrino is that they're, the experiments that look for dark matter sometimes are a lot like the experiments that look for neutrinos. So since I worked on neutrinos, it's almost like I'm ready for a dark matter experiment as well. And this would be sort of in the realm of astronomy and particle physics, of course, if you're trying to find, like, say, for example, we didn't really confirm this. There is another candidate for dark matter. It's called WIMP. So after they realized that neutrinos are too low mass to be dark matter, they theorized a particle, which is kind of like the neutrino. It's also weakly interacting, but they, in their imagination, made it more massive, because it's kind of like taking a neutrino and imagining what if there was a particle that was more massive. So they called it WIMP, weakly interacting massive particle. So, if we now do an experiment for WIMPs, to search for WIMPs, much like kind of how we do experiments to search for neutrinos sometimes. And neutrinos are confirmed. Neutrinos are definitely a thing, and yet they're very difficult still to observe, depending on which ones you're trying to get and stuff like that. So pretty much in that same realm of things, you might see that you might be able to set up an experiment which would search for something like the WIMP. It would not be the exact same experiment, but it's giving you sort of an idea, right? Like, this is sort of what we're after. So there is such experiments, and they're still underway. They're still, working on it. And if they successfully, for example, find the WIMP, then they would have to take data, analyze the data, and statistically significantly say that they found the WIMP. And for that, they would probably need some signature that the WIMP would make. And if they found that signature, and if it was confirmed with enough data and statistics, then they might be able to say that they found a WIMP. Now, this has not been done yet. So that's why we say that we don't know what dark matter is. But this is sort of the approach of trying to find dark matter. For example, with the WIMP, there are other candidates of dark matter too, yet other candidates, which would be different. But this sort of work would be done in the cross-section of particle physics and astronomy to give you dark matter results. And even if you say, it's very common in these types of experiments to not find the thing you're looking for. So then what you do is you place constraints on the theories that predict that thing. So even if they don't find a WIMP, they can still say something useful about the WIMP. Maybe the WIMP doesn't exist, maybe it does exist, but this experiment could not confirm its existence, and it could not confirm, we looked at this, and this, and this, such a big volume of this and this. It could be ice. If it's in Antarctica, there is an experiment actually in Antarctica that was at least setting up. I don't know if they did a run or not yet, but in Antarctica, people like to use the ice a lot. There are other detection medium possible too for this same category of experiments. I'm not saying particularly now, I'm just giving a broader example. You could use water. Like, there is an experiment in the Mediterranean Sea as well. So that's in the northern hemisphere. Overrated hemisphere. We like the Antarctic or the southern hemisphere more. Less noise there for experiments. So, things like that. So you can do these experiments you don't necessarily have to do it with ice. You could do other things: salt, ice, water, things like that. Greenland is another location. Again, sort of an overrated hemisphere. It gets in the way of Greenland sometimes, but it's a not bad place. Antarctica is lovely, though. Lovely. Just a whole continent giving you so much scope. So, a lot of these experiments are in Antarctica. And again, I'm biased. Somebody who works on GNO, Greenland Neutrino Observatory, will probably not like this comment. So, just know that sometimes the material you read about is probably biased. I am a little biased, for example, towards neutrinos in Antarctica. But not really towards neutrinos in the sense of dark matter, because I don't expect neutrinos to be dark matter unless it's shown, with obviously a lot of proof. But if an experiment that is looking for, say, the WIMP, and it's similar to a neutrino experiment, finds that to be, finds a WIMP and finds basically confirming that there is such a thing and it's dark matter, then yeah, that would be a cool result. But the point is, that would be a really cool result. But the point is, even if you cannot find it and you say, oh, we looked and we looked and we looked for this long and at this much ice or whatever else, and we didn't find it, you can actually place a constraint on your WIMP flux or WIMP amounts to say, well, your prediction or your theory said the WIMP would do this and there would be so much of it, but actually we didn't find any. So you're freaking wrong. And this theory needs to be updated. So experiments help a lot with updating and correcting theories and also confirming them. A theory is just a theory until it's confirmed with an experiment. So things like that. Did you get radio waves from the ice? Yes. Groove 2, did you go to bed? Ace Wolf Peach says, did you? Did you get radio waves from the ice? Yes, I will tell you about that. Have a good day tomorrow. Hi Gladys, thank you for joining the live. Sorry I missed your message. Thank you for joining. Do check us out and go to our live tab and hopefully you can see the whole video there. Did you get radio waves from the ice? Can you chain react particles in the atmosphere in chosen areas? No, that's very difficult. I mean, I can't. So there are air showers sometimes from charged particles in the atmosphere. So actually, you bring up a good point. Air showers is another way of detecting something like a neutrino or cosmic rays, actually. Has anyone done any work on dirty thunderstorms physics? I don't know what that is, so I don't know. WIMP is a crappy name. Should have called it Bistrino. Oh, Reese, you'll like this. So, guess what? Because one of the candidates is called WIMP, the next candidate, once they establish that WIMP is a candidate but we haven't seen it yet, guess what they named the next candidate? It's kind of related to your comment. So, I know, the WIMP, well, weakly interacting, right? The WIMP comes from being weakly interacting. It's people taking out their frustration on the name of a particle. Simp. No. Simp, I wish. That's too funny. Oh my God. So actually, you know what? Let me read this paragraph. You'll like it. Although WIMPs have been searched for in particle accelerator experiments, they have not yet been found. Of course, since their predicted rest mass is quite large, typically the numbers are around 100 times the mass of the proton, you wouldn't expect to produce them in the current generation of accelerators. However, the Large Hadron Collider at CERN is expected to search for supersymmetric particles with thousands of times the mass of the proton. So some Susie stuff there. Other experiments are searching for WIMPs in the same way you detect neutrinos by building a really big detector and waiting for those very rare interactions mediated by the weak nuclear force. So see what I was kind of saying about neutrinos. The same way they expect to see neutrinos, sort of similar, looking for very rare interactions mediated by the weak nuclear force. That is basically the definition or how one would describe neutrino searches as well, but it would apply to the thing called WIMP. which is a theoretical particle. So far, there exist only upper limits on the WIMP interaction rate, but the search goes on, dot, dot, dot. So that's what I was saying. When you don't find a WIMP, you can basically put upper limits on its interaction rate or something, so that you can say, well, we didn't find any, man. So, like, we tried and didn't find it. So here's your upper limit. Okay, the third candidate, pathetically, oh my God, pathetically interactive. Pimp. No, so the WIMP has misled you. WIMP, WIMP is like a WIMP. Oh, they're a WIMP. It's kind of related to that. It does not rhyme with WIMP. But I like the guesses you're coming up with. WIMP, simp, and pimp. Pathetically interactive. That's good. Yes. So the third candidate, at least in this textbook, which is a textbook for astrophysics, so don't come at me. And I know the authors, they're very nice people. So in this textbook, the third candidate is something different. It's called the macho. Get it? So WIMP is the WIMP. WIMP is a WIMP, and then macho. So they named this other candidate probably because this is a different group of physicists who's like doing this particular candidate and who wants to go after this particular candidate's potential existence or not. So they named their own candidate macho, because why not? Because it's going to be the WIMP versus the machos. So physics is all about this type of, little competitions. The term macho is a slightly strained acronym for how can you harness and electrify an air shower. They definitely did their best to make that fit. Exactly. So the term macho is a slightly strained acronym for massive compact halo object. Look at this. Look at how much they tried. Massive compact halo object. So basically, this is just saying that maybe there are some dim, dense objects that don't contribute to the luminosity, but they're out there. We can't see them very easily, but they are going to be massive and they are compact and they're not very luminous. Because, if it was like a whole star, stars would have luminosity. So they're going for something like a compact object or sort of like maybe like a stellar remnant, and they're going for sort of a twist on what we know stellar remnants are like and calling it the macho. Brown dwarfs, old cold white dwarfs, neutron stars, and black holes can all be machos if they're located in the halo of our galaxy. So then they go on to try and find the machos using gravitational lensing, and they didn't really find machos. Only 20% of the dark matter in the halo can consist of machos. There's still plenty of room for WIMPs in the galaxy. They didn't find WIMPs either yet. So who knows? Who knows is the answer. Ace Wolf Peach is asking, how can you harness and electrify? We can't. So far as I know, these answers are really discouraging. Particle astrophysics experiments often lead to upper limits and constraints. Like I was saying, we can't always find the thing we're looking for. Sometimes we find the thing we're looking for, or we find a different thing that we were not looking for. For example, my experiment was designed to find neutrinos with radio waves, right? As in, the interaction of the neutrinos would give us a signature, which would be radio waves coming from the ice. And so we point our horn antennas towards the ice and we hope and pray for something, which is not noise, which is, of course, we get mostly noise. And there's a whole story about how then we would find the actual signature. But the name of the game is to kind of, analyze and figure out what's noise and not call it a neutrino. But actually, what we found is that we were also a very good detector for cosmic rays. So some cosmic rays, many cosmic rays do air showers, and we were able to pick up this signature in an opposite polarization just by chance, just by sort of how our experiment was designed also allowed for the finding of cosmic rays, and we were able to measure some really cool extragalactic cosmic rays instead. So sometimes you look for one thing and you find another, and this is sort of a definition of that. Basically, we have been looking and looking and looking for neutrinos. We've written a lot of papers. We've carried out a lot of searches and published them, so they're in the public domain. But the particles that are confirmed and that are sort of candidates of anything would be cosmic rays, actually. The nature of those particles that we've found are cosmic rays. I have some of my own that I found as well. It's in my thesis. One of these days, I'll read my thesis. I'll reference my thesis and we can get a better idea of all this. But yeah, so you bring up a good point of these air showers, and obviously air showers too can be picked up by something like a radio telescope, because if you get the signature in the other polarization, which is really coming from the air shower, then you can detect those as well. And you were asking whether we can, because we know that our, for example, the Earth, our atmosphere, is constantly getting bombarded with cosmic rays. It's a very common thing, actually. Now, getting the extragalactic ones or the special, more high energy ones is more special. It's not as commonplace, but in general, I don't think we've been able to harness the energy from them, at least not that I know. How can you harness and electrify an air shower? We went over that. Does the magnetosphere deflect these particles or would-be particles? Maybe they should look for them in space or using high altitude balloons where there's less noise. So I worked on a high altitude balloon. So the experiment that I've been talking about is a high altitude balloon, actually. Thank you for the suggestion. Yay! You are on the right track here. That's why I worked with NASA. NASA is the one who helps us to launch these high altitude balloons. They're almost going to space. So first you have to make an instrument that will work in basically space. That was a lot of fun. And then you do tests to make sure that it can actually fly and things like that. And then you actually go get it ready for flight and fly it. So yeah. Ooh, actually today is what, December 4th or 5th or something? December 3rd was the anniversary of my first flight. Yeah, it was around now that we launched 8 years ago. Maybe they should look for them in space. But that is not to say that we were not really looking for neutrinos. So this high altitude balloon experiment that I just mentioned, it's high altitude balloon so that it can survey more ice. It goes up and it surveys a larger amount of ice at any given time. Because in these experiments, the name of the game is your instrumented volume. You want, so say your detection medium, where you're hoping for the interaction to happen, say that's ice, in this case, Antarctic ice. Then you would want to instrument as much Antarctic ice as possible. So what we do, we put our detector, we hang it from a gigantic balloon. This balloon is like larger than a football field. And we utilize the polar vortex to make it have basically circular like orbits over the continent of Antarctica with its radio horn antennas kind of looking down-ish towards the ice to get a certain geometry of neutrino interaction signature coming from the ice. It's all very specific. It's not going to work for a bunch of neutrinos, but it works for certain, it's theorized to work for certain neutrinos. And you're asking about the energy. How does one differentiate these high energy particles? Do they have specific signatures? Like how would you know if you found one that hadn't been previously detected? Yes. So not all instruments are sensitive to all types of energies and particles. I have a slide on this I should show you. Basically, we are sensitive to this instrument that I just described, and there's details of why and math of why. But basically, we are sensitive to ultra high energy neutrinos. We're not sensitive to, or at least not that I know of, because we haven't, you know, published and discovered and analyzed any such thing yet. Because we've done a number of searches and we have not found any lower energy neutrinos, nor are we expecting to be sensitive to them. So basically, our instrument is not sensitive to lower energy neutrinos, like, say, for example, solar neutrinos, like the neutrinos that are constantly going through us from the sun. Those are very low energy neutrinos in comparison to the ones of interest to me, for example, for my PhD thesis. So depending on the source of your neutrino or other particle that's of interest to you, and depending on your sort of depending on where you think it was made, basically, because you're trying to see a particle and then you're trying to track it back to its source and learn something about the source, right? That's where the astrophysics part of it comes in. So nice thing is, so you asked about the magnetic field as well. Neutrinos do not interact with the magnetic field. Neutrinos are leptons that only interact through the weak force. They're weakly interacting. Same way for the WIMPs. The WIMPs are theorized particles. They're not real yet because they haven't been found yet. The dark matter candidate that's a WIMP would be sort of similar. They would not interact with the electric and magnetic fields at all, and they would not get deflected, for example, by galactic magnetic fields and things like that. So it's kind of nice. A neutrino, when you get one, should be pointing straight back to its source because it does not interact much with anything on the way, and it does not get deflected by magnetic fields. So this is something that makes them better as an astrophysical messenger. But what makes them difficult, of course, is that they're just weakly interacting, period. So even your experiment is going to have a hard time detecting them. How does one differentiate these high energy particles? Yeah, so I just answered that. So basically, there are other experiments too in Antarctica. One of them is called IceCube. This is probably the most famous one in the neutrino world for astrophysical source type of neutrinos. This experiment has actually measured a number of neutrinos, many neutrinos that are astrophysical in nature, but they are also sensitive to a more lower energy neutrino than the experiment that I was working on. So basically, these more PeV scale neutrinos would be something that IceCube is sensitive to, and they got a bunch of them. Their way of detecting the neutrinos is also different. They use optical light. They don't use radio waves, and they instrument a cubic kilometer of ice at the South Pole, and they instrument it very differently. They use PMTs, photomultiplier tubes, and their whole their whole approach is different than ours, and they instrument, of course, a different volume than ours. They instrument a smaller volume, but they're really good within that smaller volume. And of course, if your smaller volume can still catch a bunch of neutrinos because the neutrino you are trying to catch is of lower energy and therefore not as rare, and you do a good job of it, then it's good. So that's what IceCube is. Oh yeah, no, that's all good. So they have found machos. So not really. So machos, I mean, there are some dimmer objects in the halo, maybe that could contribute to around 20% of the dark matter in the halo, but they don't think that machos are a one and done candidate either. So they considered the macho, which is massive compact halo object, basically dimmer type of stellar remnants-ish type of things. Dimmer, remember, it has to be dim because, if it was bright and contributed to luminosity, then we would know it was there. And the whole point of this thing is that we didn't know it was there. There's this mass that we didn't know about. So it has to be something that is confusingly dark. And so they are thinking up, imagining up a type of object that could somehow be both massive and compact and dim, and they came up with this, and they called it macho. But after doing some experiments to confirm this, and especially by using gravitational lensing, because basically a macho would act as a gravitational lens to some distant stars. So by observing what happens to starlight because of a macho, you can basically figure out how much macho there is. And they found that if there is machos, they only account for around 20% of the dark matter that was considered to be in our halo. And so macho cannot be it. There is still something more that is out there that we don't know what it is. Yeah, so that's what it is. As in, we don't know. Photovoltaic multiple PMT. I said PMT. Hey Google, what is a PMT?
According to Wikipedia,
There you go.
photomultiplier tubes are extremely sensitive detectors of light in the ultraviolet, visible, and near infrared ranges of the electromagnetic spectrum.
So yeah, I said PMT. I don't know if the word voltaic is part of that or not. I forget. So their impact trajectory would point to their source. Ah, okay, I understand. I mean, I don't really understand because this is like stupidly complicated and I'm drunk, but yeah. Sort of, yeah. I honestly, if I read about PMTs, it'll probably jog my memory, but I didn't work with PMTs. So, I kind of forget exactly how they work. I should probably look it up and tell you, but IceCube has PMTs, pretty much. So, but yeah, basically, if you found a neutrino and you knew sort of where it's a lot of math and geometry math to figure out where did I see it coming from, where did it interact, what would that mean as to which direction it came from. But then in the case of the neutrino, unlike cosmic rays, you would actually know that it points back to its source because the neutrino does not interact with other things. Also, why is it important that the neutrino does not interact with other things? Because, when you're getting a neutrino of a certain energy and it did not interact with other things, then it's likely that it points back to its source because it's rare to find such a neutrino, but if you have, then it's likely that it points back to its source because basically if it interacted with a lot of other things, then it would have interacted, and what you're getting is a neutrino from some other process. And say it did interact because it's high energy and it loses some of its energy or something, or basically cosmic rays, especially because they get deflected, because the other candidate for particle astrophysics is cosmic rays. And cosmic rays, unfortunately, they get deflected a lot. They could, you won't know the exact direction where it might have been coming from without doing something much more complicated. So, in the sense of comparing with cosmic rays, neutrinos are really good at pointing back to their source. And so the ones that IceCube found, because IceCube actually found a number of astrophysical neutrinos, that would be a good way to do astronomy with neutrinos and sort of getting confirmations of some of these other things, like we saw gravitational waves from the LIGO experiment. So it helps us to do these cross experiment and cross field type of things. Like one experiment gives us something from an event. If IceCube can also give us neutrinos from that particular event, because it also produced neutrinos and IceCube was able to measure some of them or one of them or something, then it gives us a fuller and fuller picture in astrophysical world about what happened. Did you say photovoltaic solar panel tubes? I've had a few X's with PMT, but not that PMT. I've had a few examples, you mean? So, did you write papers on graphene also? Nope, I did not write any papers on graphene. Sorry. I'm not an expert on graphene enough to write a paper on graphene. Absolutamente nada. Never, 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 never. Not yet. I mean, never say never, but not yet. I don't have any papers on graphene. Could dark matter comprise of a combination of these high energy particles? Or is it believed that one type of particle is responsible? So that's a great question. It could easily be a combination. At this point, Reese, anything is a good, is fair. Because we continue to not find what exactly it is, if you have a reasonable sort of a theory where you're like, okay, I think dark matter is partly this, partly that, and this is my theory, and you want to go out and test it, that's fair. At this point, basically, we were looking at the candidates here, right? They were saying that, oh well, if it's neutrinos, that would maybe account for a very small percentage of dark matter. Oh, if it's machos, then it accounts for around 20% of dark matter. You know what I mean? Like, so it's not that machos are completely written off. It's just that it does not account for the large majority of what dark matter is. So we still have a problem. That's what it is. We still have this issue of not knowing what it is because we don't account for most of it. And well, what is most of it made of? Because it's not machos, it's not neutrinos, and WIMPs we haven't found yet. And there could be other candidates too in other materials that we cover. But basically, that's sort of the status. If you came up with a theory that sounded pretty reasonable, as far as you say for some reason, you'd have to give a reason probably. Like, say if you had a reason to believe that dark matter is actually this amount of neutrinos, just as an example, and this much other stuff, where the other stuff is some particle that you imagined and now you want to find it. I mean, yeah, that could very well be a plausible theory. What's the chance you have an XRF mass spectrographer lying around? Not here, but there's there are a lot of toys at the labs that I've worked at. So yeah. Yeah. So actually, what you said, Reese, is a very reasonable thing to say. I was thinking the same myself, which is that why can't it be a combination of different things? And pretty much, I would not be surprised at this point if it were. If they find that actually it's like this thing and this thing and this thing, honestly, that's not that bad. Maybe, maybe we just don't know. The uncomfortable answer is that we don't know, but that is the truth. So I always say it on the channel, which is that we don't know. So if you want to work on it, feel free, be our guest. And yeah, we don't know. Same thing with dark energy. We don't know. There are important questions that are still unanswered in physics and this universe. So we have been covering a lot of topics, and I covered a little bit more, gave some more context about my own thesis work as well today, which hopefully gives you some idea. Especially the neutrino stuff is important and relevant because it kind of lets you get a peek into dark matter as at least as a dark matter candidate, and also the same. Sometimes it helps because the same sort of experimental approach that you have for one thing might apply to another thing, and a lot of experimentalists actually leverage this. Because doing experiments and making instruments is very difficult. So whatever they learn from one part or one experiment, they basically try to apply to another part as they discover more and more questions that are not answered yet, you know? So I could totally see how something like a dark matter experiment could really be sort of an offshoot of a neutrino experiment, where the candidate was a WIMP, that is. If it's a completely different candidate or thing that they're thinking about, then you would probably need a different approach. Or maybe not. Maybe I'm crazy, you know. It could be ever do calibration papers. What's the chance you have ever do calibration papers? I have I don't know if I have a paper that's all calibration. We definitely had to do calibration work in our experiment. The unknown aspects of science are very attractive, as are you. Oh, thank you. Wait, did I say that? The dirty thunderstorms are the explosion, and the physics are beautiful. Look at the pictures of a dirty thunderstorm, and you will understand when you see the lightning it creates. No, no, no. So, but yeah. Oh my gosh! Oh my gosh, it's working! Hello? Can you see this? So, YouTube apparently lets me. Hello? Hello? Can people see this? Is this a thing? Is this a thing? Oh my god, I think it's a thing. Can people WB? Can people see me again? So I tried to check my message and I killed the live. And then when I tried to make a new live, YouTube offered me very kindly to just continue my live. So thank God. So, because that would be really bad if we lost our precious chat and precious discussions here. Thank you. Sorry the live got killed. It's all good though. But yeah, no worries. No worries. We're being watched. No worries. Thank you so much, everybody, for being here. We're back on the live and whatnot. And actually, oh wait, no, I can't actually share it from my phone. I don't think I ever shared the live. Sorry about that, everybody. If you did not get to know that we're live, we have been chatting and I didn't even share it. So anyway, yeah, I went to New Orleans. This is why I was gone for a while. I made a impromptu plan with my friends. So I did Thanksgiving with my friends. And then they told me that they're going to New Orleans. They checked flights out of Boston and they found that the cheapest one is to go to New Orleans. And none of us had gone to New Orleans yet. It's a very important city with a lot of history. So we just impromptu went and I joined them a little bit later. So that's why I was gone, but happy to be back and happy to be rested and sort of getting back into things again. I don't know. I'm feeling very tired. Is anyone else tired from this year? I don't mean right now, but basically because it's December, I suddenly feel like I've hit a wall and I cannot keep going anymore with things. I don't know if you feel that way or not, but basically, yeah, that kind of happened as well. But here we are. We did it live today. Thank you to everybody for joining today. We recapped 20th century, 21st century physics. Yeah, I can relate. Yeah. We talked a little bit about my thesis and whatnot. and neutrino physics and how to detect neutrinos and how that's kind of related to dark matter depending on the dark matter candidate of question. But yeah, I love talking to everybody about these topics. So if you have any questions or comments or side comments about this, let me know. It helps to keep the conversation going and the topics going. Yeah, I can relate. Yeah. Reese, how is your business going? I know you were working on setting up something new. Hopefully that's all going really well. But yeah, I think this month too, I will be going live a lot. I have some goals that I want to fulfill with my YouTube channel. And although I'm getting closer and making progress, I'm not quite there yet. So I really appreciate everybody's support during the live streams and also towards my videos and shorts, which I will be publishing more of in order to make my channel keep going, keep on keeping on. So thank you. Thank you, everybody. Here is Baji. He is doing the thing where he relaxes. Reese says, going well, just finalizing things at the moment. Thanks for asking. Yes, of course. I am happy for you. That's exciting. Ooh, also, I know that some of you guys have been catching my lives after they're posted already as a video, such as Heike. So thank you for doing that as well. Thank you for catching up with our lives. Even if you have to do it later on, we really appreciate it. Yay! What did I write just now in my channel? We are live. Join us. Okay, good. I wanted to make sure that I didn't write something weird by mistake. Yeah. Yeah. Bless you. Oh, thank you. Yes, of course. Love it. Love the updates. Love catching up with everybody. Indeed. It's been nice to catch up today. Sometimes I go live and I don't really find my usual physics group of people, and it takes a little longer to get into the groove of the discussion. But when people like you or some of the people who are asking or saying more of the science stuff joins the live, it can go a lot better actually. Kind of helps to momentumize the discussion. So thank you. It's very cold now in Boston. I'm worried about my gas bill, I will say, on a different note. Tomorrow, it's supposed to snow starting 6 in the morning. So I think tomorrow I will go live during the day because, like, I'm not going to go outside. So might as well. And yeah. How is the weather in the UK? We've had snow over here too. Wow. Yeah, we're all getting snow, aren't we? Ooh, also, I forgot to mention that we did sort of an introduction to astronomy recently that people really enjoyed. So we might even do some of that again soon. We've had snow over here. The bunnies water dispenser thing froze the other day. Oh no! The bunnies water dispenser thing. Oh my gosh, like their water froze? That's so sad. So I guess it's kind of like your morning now. Like 7 in the morning maybe. Poor Bunskies. Yeah. Well, do they mind if they have a little salt in their water? Because that's what I could think of to keep it from freezing. Doing some physics on the go here. Because I asked if we can hang out for a little bit longer because 7 nearly, yeah. Okay, let's hang out for some time if you're around because I want to make some tea slash a warm drink, maybe a hot chocolate or Horlicks because I'm like kind of freezing. So I kind of want to keep chatting with everybody and make myself some boiling water. I just kept defrosting it with warm water. Oh, good. That's good. Maybe we could look up if rabbits can, well, don't do it. It might be dangerous for them. I don't want to suggest something like, say, like, having salt in their water, because I don't know if that's like bad for them somehow. But that's too bad if they're getting, that's like one way I can think of. Tea is a good call. Might join you there. Yes. Yes, please do. Indeed. Let's make tea and let's have tea because I'm insanely cold actually right now. Look at Baji. Little blanket. Baji. So most cats actually get kind of freaked out. Um, but Baji likes the blanket. Coffee. Yes. I don't want to do coffee because I do want to sleep tonight, but yeah. Tea starts wars, people. Yeah. Ace Wolf Peach, thank you so much for your comments today. Thank you for participating in the live. It really helps us. I want to bring them in the house, but they smell. Oh, yeah, I know what you mean. They do smell. I have visited bunnies of my friends, and they do kind of smell. Coffee makes my heart go weird. Yeah. I mean, yeah, it does increase your pulse, right? Thank you. Tea starts wars. I don't know why. I feel like I don't really get it. Is this a British thing too? Or, I mean, I'm Indian, but I have enough of the British, whatever, influence and whatnot to not really understand this. Does like tea is huge in India and in the UK, I think, too. Is there something more? British Empire was built on cups of tea. Yeah. Exactly. Indeed. Okay. Ooh, you know what? We can look at the blue light of my teapot slash boiling water pot. Are you British, Ace Wolf? Red Bull and Reese cups makes me break out in speeding tickets. No, Ace Wolf is American. I could just tell. Yes, I'm from Kentucky and the Army of North Virginia, lol. Yeah, no. Ace Wolf has sounded like an American for a long time now, which is not a bad thing at all. I like it. Good. We have Americans, we have the Brits, sometimes we have Japan, South Korea. Oh boy, I wonder what the South Korean news is. Today, our South Korea news person did not join, or at least they didn't say hi. BJ sometimes joins from South Korea. Also, we have Finland, we have Germany, and other countries too, Poland, but I haven't seen too much else today. Yes, physics has no borders. Ha ha ha. Yes, love it. Yes, indeed. Thank you. Yes. Okay. Let me get up. Oh God, it's very difficult to get up because this couch is not easy to get up. Oof. Oof. All right. Okay. Why didn't I bring my velvet purple thing down? I'm so cold downstairs. It's so cold. And I went swimming and I showered, so that's why I'm also cold. We will do the normal thing of charging my phone by the whey protein you guys know and love. Ah, cool. Physics has no borders. The dragon guy who bans people for nothing isn't here. He's funny. Oh, yeah, Reese. I did something bad. I got a little tired of the dragon guy banning my favorites. And so I took him off of the moderator thing. I'm a little sad. I didn't want to ban the ban guy, and he has banned some people who definitely deserved it. But he was being so, like, he loves to ban people, you know? He was here earlier, actually. Dragon, are you here? Say hi. Dragon, if you're here, we miss you. Switcheroo, what does that mean? Banish the ban guy. Yeah, he was even banning my favorites from the UK. There's a few girls who joined from the UK and we have a great chat, but he was being very harsh to everybody because he was bored. These lives don't have as much drama as Dragon can slay. Let's just say. Ooh, that rhymes. Yay, yay, yay. Oh my god, it's goofy hour, guys. Who wants to say a goofy thing or two? Okay. I need my jacket. I need my jacket. It's so freaking cold. Oh. Ah. I'm laughing still about the dragon slaying. Oh my god, it's so cold. It's so cold, it's so cold, it's so cold. Oh wow, I'm stumbling about. Here. Hello. It is I. We will make some tea. Hello, everybody. We are now going to look at the ceiling, charge the phone. I will make tea, and we will keep on chatting. Thank you so much for being here, everybody. There she is. Yes, I'm here. Hello, 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 hello. Hello, my friends. Here we are. Here's the, look at this. Here's the teapot. We're gonna be boiling water in it, and it turns into a pretty blue. So I will start this process now. Please, heater, start to heat the house here. You know, what I'm realizing is that this volume of air is very difficult to heat. And it gets very, it's so cold because it's hard to heat this all up. Okay, all right. Mr. and my friend went to the casino on the way to the taxi place. I've somehow come home with more money than I went out with. Mr. and my friend, me and my friend, went to the casino on the way to the taxi place. I've somehow come home with more money than I went out with. Oh my gosh! Wait, you made money at a casino? That's amazing. That's okay. You're doing great typing. Given the circumstances, I think it's great. I need an XRD XRF mass spectrographer. If anyone has leads on one, used or a used one, any labs are changing out. Oh, good. Okay. Yeah. Thank you for the question, Ace Wolfpack, or not Wolfpack, Wolf Peach. I say Wolfpack because I was part of a Wolfpack. Yeah, I went on roulette, but I didn't have a clue what I was doing. I will certainly announce it on here if a mass spectrographer ever becomes available that I know of from any lab or anything like that, because that's a great question. Yeah, I will definitely assist you in your hunt for one if I can. I haven't been in there since 2014 or something, apparently. I went on roulette, but I didn't have a clue what I was doing. I don't know what roulette really means. I have heard of it. How do you play roulette? Tell us. We just learn things generally here. I was banned. Oh my gosh. Oh my god. There is some drama here. I was banned for fighting back then, but they let me in today. You were banned since 2014? You fought? Who did you fight? You have to tell us the story now. Tell us, tell us, tell us. There's like a spinning wheel with 36 numbers, and you have to bet what number it lands on. Oh! Thank you for telling us what roulette is like, or what roulette means. I don't think I knew that. Although I've seen it in the movies. Okay. Facebook. So one night I saw him. Wait a minute. I gotta read this. 1 second. Give me 1 second, guys. This has to be read with relish. Oh gosh. Okay. I am so cold. Seriously. Basically, a girl I was with left me for another guy who I didn't know at all. And he started messaging me on Facebook saying that I was just a little kid and he was a real man and stuff. Well, he sounds like a loser. So one night I saw him in the casino with some other girl. So I walked over and kicked the table over and punched the guy. Wow. Facebook? He messaged you on Facebook? Like, for what reason? Why would anybody do that? That's crazy. So he was jealous. He's a loser. Facebook, bah ha 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 ha. Yes. What a weasel. I was with this girl for 5 years from the age of 15 and was in love with her. Oh. Oh, wow. That's a bummer. Should have kicked his ass twice. Yes. Ace Wolf, please tell him what would have gone down in the US about this. The whole Facebook thing. Tell him, Ace Wolf. I love it. There is some drama. There's some, well, not drama in the chat, but drama is being discussed in the chat. Kinda love. Kinda sorta love. As I make my, look at this. As I make my tea. See, it became very blue now. Should have kicked his ass. Indeed. Apparently, he was a guy who was renowned for getting with girls on the rebound. Another guy I know beat him up too. Got a similar thing. Over a similar thing. So by the time you're beating him up, he's with a different girl, but he's messed up the relationship and messaged you on Facebook. That is some weird behavior from the guy. This guy is really something. I don't understand. Yeah, no, I don't understand. Indeed, I don't get it. Why would he bother? Look at Baji. He is so tucked in. It's so cold in Boston. Baji's in the blankie. It's so cold. It's so cold. Hi. Hello. Thank you for joining the live. Hello, hello. How's everybody doing? We're just chatting at the moment. We're gonna be making some hot water, boiling water, and then we're gonna be, ooh, look at the bubbles form. Little bubble. It gets even crazier. So one night I was at a house party at this huge mansion house, which had a large glass dome ceiling. Large glass dome ceiling. Over the dance floor, and all of a sudden there's a huge crash. What? It gets even crazier. So is this related to the guy whose behind needs to be kicked? Ace Wolf Peach said something. What on earth? What on earth? Okay, let me show you what I'm about to drink. This is Horlicks. It's a classic malt. This is from India. It's a thing I grew up drinking, so I will continue to drink it now when I find it in an Indian grocery store. Okay, let's see. What is it made of? Oh, let's try it. Oh God. Some guy. It's 2:07. Some guy had scaled the roof and jumps through the ceiling. Onto some poor girl who ended up in a wheelchair, and the guy had bad injuries, and it was the same guy. What are you saying? Some guy. All of a sudden, there's a huge crash. Large glass dome ceiling over the dance floor. First of all, that ceiling sounds like something else. Scaled the roof and jumped through the ceiling onto some poor girl, and it was the same guy. You know, the casino should definitely shouldn't have banned you. They should have banned him, knowing how crazy this guy is. They should give you an award instead. Karma was a failed suicide attempt. Well, that's so messed up. Hot mess, like hot garbage. God knows what my ex saw in him. Oh. Well. Hi, Baji. Did he have syphilis or something? Some type of encephalopathy. Encephalopathies. Yeah, that would be bad. Probably. Oh my God, but that's so dangerous for everybody that he's involved with. Gosh. Cute, Shona. Hi, Baji. Baji wants attention. Baji. Why jump onto a room full of people dancing at a party, though? That's just insane. For attention, I think. Yeah, he chose a very public event to do this, right? She said it, attention. Yeah. It's basically, yeah, you could do it quietly if you didn't want attention. Yeah. Too bad that he injured people. That's not, I can't believe such people are even a thing. I mean, I can believe it, but I can't believe how bad that is. Baji! Baji Baba? I think Baji is like quietly. Yes. I could have done it quietly. I had to attend a police interview for punching him and was charged with battery or common assault. And when she ended the recording, okay, you're gonna continue, good, of the interview, she said, the guy sounds like an asshole. I think I'd have punched him. The guy sounds like an arsehole. I think I'd have punched him also. Oh my God. That's a really good story, Reese. Thank you for sharing. Wow, I can't believe you went through that. You've lived a life, man. Yeah, I got 4 charges right now myself. What? What did you do, Ace Wolf? You got 4 charges? Why? Who are you beating up? You know, I don't know why this live does have some violent people, I must say. There's a girl on here who's usually coming in and saying that either she got punched or she punched someone, and I like her very much. I mean, she's a great person on these chats. I think she's great, but she's usually been punched or has punched someone. So honestly, you guys are a violent lot, I must say. I must say, we don't do anything violent. The funny thing is that the lives are very non-violent and soothing. But hi, Sofyan. I've been in court every month for the past 8 years. What? But some of y'all really do be violent. I implore you to please stay out of jail and be in the live more. Oh my God. I'm sleepy, but your stories are interesting. Wait, where is my false acquisitions? I know, I'm just joking. Yeah, I figure. Not violent, to be honest. I was raised in a rough council estate, social housing estate. So obviously, I've had a few fights, but I'm not violent at all. I actually also have had a few fights, but I'm also not violent. So there we go. We're all 100% been in some fights. False accusations of what, Ace Wolf? Yeah, man, we gotta know this now. Don't keep us hanging. It's so cold. What were your fights about? Didn't realize just because I'm a brickyard by trade. I study physics as a hobby. I got set up by the police. Oh. Had my spine broken 5 places. Oh my gosh, my fights were just in school, man. Just some guys harassing me, and I tried to beat their ass. That's all. All before the age of 18. I went to a co-ed school with a lot of guys, like more guys than girls, because there's just more guys in India than girls because of female infanticide. But that's a detail, whatever. In general, my school had more guys. So you can imagine it was kind of like a bit crazy. And sometimes I got a little violent trying to manage my day, but it was rare, very rare. Next day, I'm arrested, no charges ever filed, taken to jail, had my spine. Then I've been into with them for past 7 years, suing 30 people in federal court now. Well, they didn't understand I can read. Oh, well, good luck with your case. Oh my gosh. Wow. Indeed. That's a lot. I've beaten 4 cases already, 4 more to go. Represented myself in court as well. Wow. Goodness. That's a lot. Just gonna sit. Sounds awful. Once the police have it in free, they can make your life a nightmare. Can't find an attorney to sue cops yet. I have another suit in business. And my business is most likely why I was targeted. Oh gosh. Baji! Baji! Come, Baji. Oh, Baji. Baji's such a good boy. Baji likes to cuddle. That sounds terrible, Ace Wolf. Flash-based meter. What? Then had to extract me. Oh. Baji's making biscuits now. I have my Horlicks. I have my mug tea thing. Alright, so tomorrow we will continue our physics topics. I think people have been enjoying the dark matter and dark energy type of topics with a little bit more context on the related work here, so that's been good. Baji, Baji, are you making biscuits? They're scared of me. That's why I'm winning. Yeah. Hope I catch your live tomorrow. Yes. Yes, please do catch my live tomorrow. Ooh, and I forgot to show you guys. We also have this book, Modern Cosmology by Scott Dodelson. This is what we will be using to reference. Ooh, I think one of you asked about this accelerator actually. So this is what we will be using to reference cosmology, or sorry, cosmology topics. Hope I catch your live tomorrow. Definitely, it's been fun. Thank you. So when we talk about dark energy, which is more of a cosmology type of field, we will be referencing this book. It's Modern Cosmology by Scott Dodelson. I wanted to show you this today, even if we don't get too deep into it today, but you know, this is a guy. Let me give you a little bit of background on him. So, and I think Ace Wolf actually asked about this particular place. So look at that. Modern Cosmology by Scott Dodelson, Fermi National Accelerator Laboratory, University of Chicago. So I think if you were asking about the accelerator in Illinois, you might have meant this one, Fermi National Lab. So I'm just showing you what's in the book today, and we will... Oh, look at Baji. He wants to eat the book. Baji! Oh, Baji wants to eat the book. So I'm showing you today because I also try to show people, like, our sources and references that we use on the channel. And because we've been using a lot of relevant textbooks, they're pretty easy to reference. I just show you the textbook and the author and everything like that. Granted, these are pretty expensive to buy. So if you were to, buy them, maybe try to go for used or something like that. Or you can use our live stream discussion as sort of a reference. So let me read the back, because basically what we do here is we choose some topics, we talk about it at length, we utilize the live stream people and their questions and discussion points to kind of keep on the conversation, and we use a lot of books as references. But I try to also give you information on the books that we're using so that you know, like, what is the source of this information and at what level things are at. So this book, Modern Cosmology, begins with an introduction to the smooth, homogeneous universe, described by a Friedman-Robertson-Walker metric. So actually, I don't know if you remember, we actually talked about this FRW metric in Einstein's Cosmos. So some of this is going to be familiar to the people who were here for the discussion of the book called Einstein's Cosmos by Michio Kaku. Of course, it covered general relativity, and all of cosmology is basically general relativity is a part of that. So that's why you will see some of that kind of topic come back here when we reference this book, basically. Ooh, and I also forgot to mention something that I've meant to mention earlier when we were discussing string theory and superstring theory as a candidate for the grand unification theory. I wanted to mention that if you're trying to take a class on general relativity, Generally speaking, generally speaking, a super string theorist is probably going to be a great teacher for that. So, superstring theorists, obviously, they have to start with the basic level of general relativity in order to build their theory upon. So, they're actually some of the best teachers of general relativity in a classroom context type of thing. So, if you're ever looking, that's one clue. I myself was taught GR by a string theorist, and he was very nice. So, anyways, we'll go back to this description. Smooth homogeneous universe described by a Friedman, Robertson, Walker metric, including careful treatments of dark energy, Big Bang nucleosynthesis, recombination, and dark matter. From this starting point, the reader is introduced to perturbations about an FRW universe, their evolution with the Einstein-Boltzmann equations, their generation by primordial inflation, and their observational consequences. These consequences include the anisotropy spectrum of the cosmic microwave background, or CMB, featuring acoustic peaks and polarization, the matter power spectrum with baryonic wiggles, and their detection via photometric galaxy surveys, redshift distortions, cluster abundances, and weak lensing. So you've heard of lensing before, gravitational lensing and such. Cluster abundances. Remember, we talked about metal abundances in stars and things like that? I think this is going to be similar to that. So, abundance here just means how much of the metals, and in astronomy, everything above helium is a metal. The book concludes with a long chapter on data analysis. Modern Cosmology is the first book to explain in detail the structure of the acoustic peaks in the CMB, the E over B decomposition in polarization, which may allow for detection of primordial gravity waves, and the modern analysis techniques used on increasingly large cosmological datasets. Readers will gain the tools needed to work in cosmology and will learn how modern observations are rapidly revolutionizing our picture of the universe. So, this is going to be sort of a foundation in the line of cosmology. Remember, of course, that cosmology wasn't really much of a field until we, of course, discovered, well, until lots of things. Observation is one big thing. We didn't even know that there were other galaxies. You know, in the last 100 years or so, we have come a very long way in observation, astronomy, measurement, things like that. So, knowing that there are other galaxies, knowing that the cosmos are so big, indeed, understanding about the expansion of the universe, the fact that it's not only stable but expanding, all of that, and of course, general relativity itself, all of that gives us a basis for cosmology. It's still sort of a lesser known type of field. Like when I was studying cosmology and I had questions, I would Google it and find more things about cosmetology. So don't confuse this with makeup. It's cosmology, and it has to do with the universe. So things like smooth universe, expanding universe, Hubble diagram, Big Bang nucleosynthesis, cosmic microwave background, understanding that. So, see, cosmic microwave background is a very large scale type of thing. So, we're not talking astronomy or particle physics like we were saying with dark matter. Astronomy is when you might still be sort of in your own galaxy, maybe the neighboring galaxies and things like that. But cosmology really has to do with the universe itself. We're talking much larger picture, larger structure. So, just to give you a flavor of what we will get into when we reference cosmology and this book here, is to kind of note the differences in approach as well. Astronomy versus particle physics versus cosmology, all different, right? These are all subfields of physics, but approaches are quite different. Okay, and then smooth expanding universe. Basically, this homogeneity of the universe, and then explaining certain things as perturbations. This is sort of an approach in cosmology that we will get into at some point. You'll see it'll start to make sense, because the universe is so old and we're just a small part of it. Basically, how we approach the universe and in describing the universe is kind of different from what you might have been seeing so far with our astrophysics, astronomy, those types of discussions, okay? Just kind of wanted to mention that. Ooh, and what is more, we will actually talk about cold dark matter. So I know we talked about the dark matter candidates from the other book that we were looking at. This was the astrophysics book. So again, astrophysics is going to have a very different approach to something like dark matter. Astrophysics, astronomy, particle, right? But what about the more cosmology approach to dark matter? What in cosmological way of explanation can we start to understand dark matter? Again, it's not done yet. We don't have a cosmology answer for dark matter either yet. But this book kind of goes into the approach for that. And so you might be familiar already with the term cold dark matter or CDM. It's a very leading theory actually for dark matter. And we will kind of get into what that even means, stuff like that with this particular topic here. And that kind of comes into the picture in the realm of cosmology versus in the realm of astrophysics. Okay, that's why we didn't really see it too much in the astrophysics book. These people are all colleagues who write these books, so also remember that they might have even discussed before writing these chapters exactly what's getting covered where. I mean, I don't know. That's just a theory. Scott Dodelson is not at Ohio State. He's at Fermi. But these people travel all the time. They meet each other. They go to the same exact freaking conferences. They're all related. They're all married to each other. I'm just kidding. They're not all married to each other, but pretty much. So a little bit of my personal side has come into the picture here, but you know what I mean. Basically, what's being covered here, that's why it's important to sit with all of the books, because what's covered here is not covered in a different book, but that does not mean that we don't need it for the fuller picture. Okay? So that's what this is. Ooh, look at this. This chapter has a prelude. I don't know what that's about, but we'll figure it out. This is chapter 7, which has the dark matter thing. 3 stages of evolution, super horizon solution, horizon crossing, beyond cold dark matter. Wait a minute, where is freaking cold dark matter then? I'm not ready for beyond cold dark matter. I'm ready for cold. Oh, there it is. So basically, I think it's going to be around chapter 3. It's been fun. Reset sounds interesting. Thank you. Thank you for joining, everybody. I think it's going to be around chapter 2 and 3, where we will see smooth expanding universe. We will get this guy's take on general relativity, because again, he's a cosmologist, so he's going to have his own way of describing it to us. Metric, geodesic equation, Einstein equations, distances. Ooh, oh good, cosmic inventory. So look at this, cosmic inventory in terms of cosmology, the way people, because sort of some of the words are the same but different sometimes. So cosmic inventory, we say photons, baryons, matter, neutrinos, dark energy, and the epoch of matter radiation equality. So this is going to be extremely interesting to think about, cosmic inventory, because we are in a way trying to get the inventory for what all things are sort of there, like what's in the universe, cosmic inventory. Let's take a cosmic inventory or a bookkeeping. So we will talk about that in chapter 2 of this book. And then we will have Boltzmann equation for annihilation, Big Bang, nucleosynthesis, neutron abundance, light element abundance is recombination, dark matter. Ooh, good. So I think we will look at dark matter, because dark matter is a part of the cosmic inventory at this point, right? So I think we'll talk about dark matter here first, and you will see how cold dark matter is this big candidate. People like it. And because probably it's still not given everybody all the answers, they even have research going into beyond cold dark matter. What happens is that when there is a lot of established research in a certain direction, even if the thing is not confirmed yet, it becomes more established. Whether you want to believe it or not is up to you, especially because, I mean, you're technically paying for all of this research, taxpayer dollars, right? And some people have a bigger tolerance for theories than others. A lot of people want to actually see the results in experiment in order for them to believe it. But all of this material is yours, It is for you and for you to understand and appreciate and learn from so that you can determine your determinations. So we will certainly cover cold dark matter, and we will also go into beyond cold dark matter because, of course, that's a direction too. But I wanted to give you some flavor of what these things are and also some of the politics that go behind these things so that you have an open mind and get a more context for what's happening. Okay. Who wants to like the live and give us 10 likes? Other than that, class dismissed. Good night, everybody. We will see you next time, which will be tomorrow. Good night, good night, good night. Thank you for joining. Thank you for chatting. Appreciate it. Appreciate it. If you could please like the live, that would be amazing, and we could get 10 or 11 likes maybe. If you want to see this video as a video upload later on, please go to the channel under the live tab and find it and leave us a comment. Thank you, everybody. Good night. Bye. Bye-bye.